Hello there. In this video, we're going to cover a modification of the idea of reneging that you might call jockeying. Some of the queuing theory people call it that, and in Q it's called that to distinguish it from reneging where you just leave the network entirely. You can start to define your own custom behavior for this. So let's open up a new file, how to simulate jockeying. Even just jockeying is probably all that I really need to remember this later. Okay, let's import the Ciw Python package. Now, what is jockeying? Jockeying is when they're basically reneging, they're leaving a waiting list or a queuing area of a node, and they're going to some other node, and you need some logic to decide where they go. Where is the location in the network that they would go next? And this is actually a kind of routing problem of defining the routing behavior when reneging occurs. So let's build this example. First, we'll start by creating a jockey class routing, and we'll subclass from leave, which normally leaves the network no matter what. And we're overriding that behavior. Let's go next node for jockeying. This is a specific method that you can implement. And we'll make some very specific thing, but usually my point with this stuff is not the example that I'm giving, because the example I'm giving, which is usually the same or very similar to the documentation example, is something very literal, like, okay, just return the second node. The point is really to say, well, you've got this context where you can put any kind of Python code you want here to eventually return what this signature requires. So that you know, so that you can define whatever routing behavior you really want to define here. Okay, so it has to return a node, and you've probably seen this many times now, but we can put, Q individual there. So there's a jockeying class. It just says that when the node that has this routing behavior is overridden, when it has this, when a customer at the node that has this routing behavior reneges from that node, in the sense of jockeying reneging, that it will go to some other node in the network, specifically node 2. So let's just see where we put this into a simulation construction. So of course we'll have some like arrival distributions, and actually I think I'm going to yeah, no, that's fine. Sure. All right, so let's go q.dists.exponential, and we'll pass in a rate of 5. And then maybe we'll say, just because we need some kind of behavior of going from one node to another, we have to have 2 or more nodes to really talk about this sensibly. We also need, at every node, service distributions. And let's make this 2, and maybe they both have a service rate, so let's grab that, and we'll switch it up a little bit. 2 and 4. Is that right? Seems right. I guess we'll find out when we run it. Okay, so then servers 1 and 1. And for routing objects, all right, now we're really getting into what's relevant to this video's topic. We're going to throw in this routing class, this network routing class, and we pass a router function class, or a class with these methods that decides. So we'll throw our jockey in. So at node 1, if they were to renege after some amount of time, instead they jockey in the sense of they don't leave the network, they actually go to node number 2. So then we'll go q routing.leave. So the behavior, if you're leaving node 2, is to just leave the network entirely. Now this is coupled to reneging, like it's kind of seen as, in this package at least, a generalization of reneging, to say, well, now we've generalized where the customer might end up going. So here we'll say, sure, 6. Oops, it's more 6s than I wanted. And for the second node, there's no reneging behavior. If you get that far, you're definitely being served. Okay, so that's as far as the model definition stuff, all that you actually need to do. And of course, we could set a simulation up, but I think hopefully it's clear enough. We won't go through it in this video, but the idea is hopefully clear, where what we're really going to have happen is, let's say that they do renege. Somebody arrives at node 1, and that 6 units of time elapse, so they renege. But instead of leaving the network entirely, we have this routing behavior that instead sends them to specifically node 2 of this network. So there they will definitely get their service completed. There's no reneging. They just need to be patient enough. And then eventually when their service is done, they leave the network entirely. Okay, so now you should be able to do jockeying and other kinds of more fancy jockeying than just this. That might be based on more detailed logic about the system. Maybe I'll just mention as a little aside, we've mentioned this weird thing before, but individuals have access to the simulation object, which in turn have, you know, access to really a whole bunch of other stuff about the system. So you can really do quite a lot with this, including eventually indirectly getting things like the simulation time, even though this method doesn't explicitly have time. And because we've got, you know, whatever classes we want, we can also set this up to have, you know, like an internal state, you know, self.state maybe is initially bound to something, some empty list or a dictionary or whatever. And that inside of here, you have, you know, like an update state, self.state or something like that. I mean, there's lots of things you can do. I'm not saying you should do that for simple examples or do it just cause, but hopefully that gives you an idea that you really have this kind of canvas to play with of changing the behavior of where customers go in your system. All right, best of luck with your discrete event simulations, and I'll catch you in the next video.